Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 4, Harmonic Constructions and the Fundamental Theorem of Projective Geometry. Section 33, Nets of Rationality in the Plane. Definition: a point is said to be rationally related to two non-collinear nets of rationality R1 and R2 having a point in common, provided it is the intersection of two lines, each of which joins a point of R1 to a distinct point of R2. A line is said to be rationally related to R1 and R2, provided it joins two points that are rationally related to them. The set of all points and lines rationally related to R1, R2 is called the net of rationality in a plane, or of two dimensions, determined by R1, R2. It is also called the planar net, defined by R1, R2. From this definition, it follows directly that all the points of R1 and R2 are points of the planar net defined by R1, R2. Theorem 10. Any line of the planar net R squared defined by R1, R2 meets R1 and R2. Assumptions A and E. Proof. We prove first that if a line of the planar net R squared meets R1, it meets R2. Suppose a line L meets R1 in A1. Then it contains a second point P of R squared. By definition, through P pass two lines, each of which joins a point of R1 to a distinct point of R2. If L is on one of these lines, the proposition is proved. If these lines are distinct from L, let them meet R1 and R2 respectively in the points B1, B2, and P1, P2, figure 38. If O is the common point of R1, R2, we then have O, A1, B1, P1 is perspective with center P to O, A2, B2, P2, where A2 is the point in which L meets the line of R2. Hence, A2 is a point of R2. Theorem 7. Now, let L be any line of the net R squared, and let P, Q be two points of the net and on L. Definition. If one of these points is a point of R1 or R2, the theorem is proved by the case just considered. If not, two lines, each joining a point of R1 to a distinct point of R2, pass through P. Let them meet R1 in A1, B1, and R2 in A2, B2, respectively. Figure 38. Let the lines QA1 and QB1 meet R2 in A2' and B2', respectively. First case. Then, if L meets the lines of R1 and R2 in P1 and P2, respectively, the quadrangle PQA1B1 gives rise to the quadrangular set Q of P2, A2, B2, O, B2', A2', of which 5 points are points of R2, hence P2 is a point of R2, Theorem 9. P1 is then a point of R1 by the first case of this proof. Theorem 11. The intersection of any two lines of a planar net is a point of the planar net. Assumptions A and E. Proof. This follows directly from the definition and the last theorem, except when one of the lines passes through O, the point common to the two linear nets R1, R2, defining the planar net. In the latter case, let the two lines of the planar net be L1, L2, and suppose L2 passes through O, while L1 meets R1, R2 in A1, A2, respectively. Figure 39. If the point of intersection P of L1, L2 were not a point of the planar net, L2 would, by definition, contain a point Q of the planar net, distinct from O and P. The lines QA1 and QA2 would meet R2 and R1 in 2 points B2 and B1 respectively. The point C2 in which the line PB1 met the line R2 would then be the harmonic conjugate of B2 with respect to O and A2 through the quadrangle PQA1B2 C2 would therefore be a point of R2, and hence P would be a point of the planar net, being the intersection of the lines A1, A2 and B1, C2. Theorem 12. The points of a planar net R squared on a line of the planar net form a linear net. Assumptions A and E. Proof that the planar net be defined by the linear nets R1, R2, and let L be any line of the planar net. Let P be any point of the planar net not on L or R1 or R2. The lines joining P to the points of R squared on L meet R1 and R2 by theorems 10 and 11. Hence, P is the center of a perspectivity which makes the points of R squared on L perspective with points of R1 or R2. Hence, the points of L belonging to the planar net form a linear net. Theorem 7, Corollary. Corollary: the planar net R1 squared, defined by two linear nets R1, R2, is identical with the planar net R2 squared, defined by two linear nets R3, R4, provided R3, R4 are linear nets in R1 squared. Assumptions A and E. For every point of R1 squared is a point of R2 squared by the above theorem, and every point of R2 squared is a point of R1 squared by theorem 10. Exercise: if A, B, C, D are the vertices of a complete quadrangle, there is one and only one planar net of rationality containing them, and a point P belongs to this net if and only if P is one of a sequence of points A, B, C, D, D1, D2, finite in number, such that D1 is the intersection of two sides of the original quadrangle, and such that every other point D sub I is the intersection of two lines joining pairs of points of the set A, B, C, D, D1, D I sub 1.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.